大家好，欢迎加入这个团体。这是第一个 Papers We Love 会议。我叫 Oscar， 这是雅欣和 Chih-Cheng， 他们都一起帮忙。这个团体的目标是让人介绍他们在研究的东西。比如说，可能你在看一个很有趣的文章，可是有一些东西你好像懂，但又不太确定。这个是一个很好的机会，这个是一个很好教学向上的机会。而且其他人也可以从这个分享学新的东西、有趣的东西，所以不用害怕。只要你觉得是有趣的文章研究，你都可以上来分享。中文、英文、台语都可以用。要是你想要跟大家分享，都可以跟我们说。我们也有 Telegram 的团体。分享完以后，我们会有一个小讨论。所以今天呢，今天有3个人会说话。第一个是我会介绍 Kademlia 一个第一期的东西，然后 Chih-Cheng 会说 blockchain and privacy， 然后 Kevin 会介绍 socialist and millionaires problem. Right, I'll switch to English. So, hi, welcome everyone. This is the first Papers We Love meetup. My name is Oscar, this is Chih-Cheng, this is Chih-Cheng, and they are both helping organize this meetup. And the purpose of this group is essentially to talk about research papers we read. And perhaps you've read some paper and you kind of understand it, but it's still some things you don't quite get. And teaching others is a great way to sort of learn about it's a great way to sort of learn and solidify your knowledge. And as a nice bonus, other people can also sort of learn about something new and interesting. So you don't have to be afraid, and you don't need to be an expert. As long as you read something you find interesting, this group is a great opportunity to share what you've learned. You can speak in English, Chinese, and even Taiwanese if you want to. If you want to speak about something, you can reach out to one of us in the Telegram group. And then after each talk, we'll have a brief discussion about the paper just presented. And today, I'll be speaking about Kademlia at HT, and Chih-Cheng will speak about blockchain and privacy, and then finally Kevin will speak about the socialist millionaire problem. So today I'm going to talk to you about Kademlia. So I'll start by sort of talking about where this sort of idea came from, how it works, and then finding some applications.
Let me move.
Oh, it didn't cut? No, it's cut.
No, it's cut, but...
I did this?
Wait, let me move this to here, and then... Yeah. And,
the space work?
space work. Wait.
Okay, no? Yeah, okay. Motivation. Boom. All right. So Kademlia is a distributed hash table for peer-to-peer networks. And it provides quick lookups and it tolerates node failures. Space?
Yeah.
Oh, all right. So let's start by breaking it apart. So what is a distributed hash table? Like a normal hash table, you store some sort of key value pairs, and the key is unique and is a hash of the stored value. And the value could be any arbitrary data. And the goal is essentially to store and retrieve some data. What makes it distributed? Well, we store the key value pairs on multiple computers. Obviously, this brings a bunch of new problems, like all of a sudden you need to have an internet connection. You need to know which computer is storing which key value pair. And you need to sort of figure out how to deal with computers disappearing. And you can also say goodbye to sort of constant time lookup time. All right, so why do you want it? Well, sometimes you want to collaborate with some other people and share some stuff. And you could do this on sort of a big machine where you have the SQL database and then you maybe do some sharding and all this stuff. But it doesn't work very well when you there isn't a big entity that's paying for all the hosting, for example, and maybe you don't want to rely on a single party to host all the data, for whatever reason. And finally, your data might be sensitive and prone to various forms of attacks. This is kind of where the peer-to-peer part comes in. We basically have an overlay over the regular internet, with equal peers providing some service to each other. And one of the initial use cases, and most famous for this, is file sharing, right? And with these considerations, it's kind of no surprise that DHTs like Kademlia first became popular through peer-to-peer file sharing applications. So paper was released 2002, and before that, initially, when you had a lot of people coming online, you had apps like Napster in '99, where you had live on a central server for lookups, and that was very easy to shut down. And you had later versions like Nutella that came a year after. They were more decentralized, but they used flooding, which is very inefficient. And it's kind of not stated explicitly in the paper, but in a sense, Kademlia and other DHTs, they came as a response to these very real-world problems. Kademlia, unlike other DHTs, have been implemented in lots of practical products. So initially in peer-to-peer apps like Emule and Nutella, and most famously in BitTorrent, but also in products like I2P. So in recent years, there's been a resurgence of peer-to-peer protocols with BitTorrent, Bitcoin, Ethereum, IPFS, and so on. And I'll talk a little bit about current use cases at the end. But let's go into how Kademlia works. So we said in the beginning that it provides quick lookups and is resilient to node failures. And to understand why, we have to understand how it works in more detail. So let's say you want to store something, like a string or a record of some kind. Essentially, you hash the data, and you get, in the case of Kademlia paper, a 160-bit ID key. And this acts as a kind of content addressable storage, and it's how you refer to that piece of data. And this is different from something like location-based storage, or location-based addressing, where you might have a URL like google.com, and the data can change beneath you. But with with the CAS, you refer to that address, to that content with its hash. So we want to store data across multiple nodes. How do we know which node should store which piece of data? In an ideal world, we would split this up, where each node stores exactly the same amount of key value pairs, and that's that. But since this is a peer-to-peer network, and nodes can join and leave at any time without permission, we need something that's a bit more self-organizing, and there's no one really in charge here. So each node essentially has a node ID, so that could be a hash of a public key that they control. And the node ID, it lives in the same address space as the keys, these key value pairs. And the general idea is that nodes with node ID that are they're responsible for content that's close to them. And the likelihood of a hash collision is extremely unlikely, and so on. So when we say a node is responsible for storing content that's close to it, we need to have some notion of closeness, what that means. And this is one of the clever things about Kademlia, and this is it's using the XOR metric for this. And I'll talk a bit more about that in a second. But it's not enough to just know which node in theory should be responsible for some piece of data. We have to be able to find that node. And this is where the routing algorithm comes in. And the routing is based on the node ID, and it's how we find a node that's responsible for some piece of content. So how does that work? So this is from the paper. In Kademlia, nodes are essentially leaves in this binary tree, and each node's position is determined by the shortest unique prefix. So you can't see it here. Why? Oh, interesting. All right. For some reason, it doesn't show in HackMD, but you can imagine that we have this black node, and then this is in this zero band. So this, you can imagine a circle around this whole thing, and then a circle around this whole subtree, and then this, and then this. And this is essentially, like if I'm this Slack node and I want to contact this node, for example, I don't have to know that node directly. I don't have to know the address of that node. I just have to know some address in this sort of on this branch, in this subtree. So for example, maybe I know 101. So the way I would essentially ask this node, and then this node would know more about its neighborhood, just like I know more about my neighbor here. So I would ask this node, and then progressively I would get closer to the node I want. And one way to think about this is that now we're in Taipei, in Taiwan, and maybe we know a bunch of people in Taipei, we know some people in Taiwan, and maybe we know someone in Asia, and someone in Europe, and someone in Earth, and so on. And I'm looking for someone in London. I only have to know someone in Europe, and I would ask that person, and then they could tell me something about some people who live in the UK, and some people who live in London, and so on, and I could sort of progressively get closer to the node I want. And that kind of gives rise to this O log n lookup time, because essentially each time you go to a closer subtree, and it's this sort of binary tree structure, right? And sort of the distance between each two nodes is the XOR, sort of the XOR operation between them. And that's sort of mathematically a valid metric. So what that means, for example, is that the distance between a node and itself is 0. The distance between a node and another node is always positive. The distance between node X and node Y is the same as the distance between node Y and node X, so it's symmetric. And it's also unidirectional, so if you have a node X and some distance D, then there's only sort of one node Y that satisfies that. And what that means is that every lookup converges on sort of the same path. And that's very useful for things like caching. So you have these hot lookup paths, and then you can cache the data along the way. And this sets it apart a bit from other DHCs like Chord and Pastry. And where you have slightly different notions or methods to sort of capture this notion of closeness, and they have slightly different properties. I should have shown this as well. Yeah, so here you can see this example, right, where you do this sort of progressive lookup to get to the node you want. So we know sort of how nodes can look up nodes that are closer to the node we want, and we have some idea of what closeness is, but what does a node itself know? So each node essentially has some information about other nodes, so it's an address and a node ID. So in Kademlia, this is like a triplet with the IP, UDP, and node ID. And then for each of these sort of possible shortest unique prefix, so 160 in our case, we keep sort of a list called a K bucket. And this K bucket contains up to K entries. And sort of a common number for K is 20. And essentially what that means is that it's kind of replication factor. So it's the number of times that we store a piece of data. And it's chosen in such a way that within a given hour, it's unlikely that a given node will fail. It's very unlikely that it's very unlikely that all nodes in that bucket will fail. And this is empirical data from IntelliNodes, and essentially we are implementing a least all LRU cache, so least recently used cache, where the oldest nodes stick around the longest. So you're sort of using this kind of Lind effect and using this property that nodes that have been online for a long time are likely to be online for longer. And this is sort of how it uses the notion of node uptime to get the desired property to be resilient to node failure. And then essentially we update these K buckets whenever we receive any kind of message from other nodes. And this kind of K bucket approach, it also makes it resilient to DOS attacks to some extent, because you can't just flush some nodes routing table with new nodes, because the old nodes have to leave the network first. All right, so what is actually sent over the wire between nodes, and what do we get back? So the Kademlia protocol implements these 4 simple RPC calls. Ping just checks if a node is online or not. Store tells a specific node to store some piece of data. And find node takes some ID and then returns this triplet of address, so IP, UDP, and node ID, of the k closest nodes that node knows about. K closest nodes that node knows about. And these sort of k nodes, this sort of comes to a reply. It could either come from a single k bucket, or if that node doesn't have all this information, it sort of picks the buckets that are close to this. Find value is the same as find node, except that if it's sort of previously stored, then it returns that value. And there's also sort of this RPC ID that's part of the requests, because these requests are asynchronous, so you know which request it is, and also to prevent some kind of forgery, you know sort of what that the request is, that the reply is the reply to your request. Yes, so a very common task comes back again and again is to locate the k closest peers of some node ID. And the way this is done is essentially that you pick up to alpha context in a k bucket, and alpha is a kind of concurrency parameter, and a common number here is 3. And then we do this sort of parallel asynchronous requests. So we take 3 nodes from our k bucket, and then we shoot them off. And then they come back with some reply, and then we sort of repeat the process again. And we repeat the process until we sort of have gotten a response from the k closest nodes that we've seen, and then we're sort of done. And this is kind of the fundamental building block, where you use this node lookup algorithm for storing data, where you do this, and then you issue a store command to those nodes that you found, and they are sort of responsible for storing that data. And it's also used for sort of joining the network, where essentially what you do is you try to find yourself. So you send this request like, hey, I'm trying to find myself, and then you get this reply from all these other nodes telling you who your closest neighbors are. And that goes back to the sort of city metaphor that you can think of, that you want to sort of know your closest neighbor, essentially. And then also to ensure persistence, sort of these nodes also republish these key value pairs, and the original sender might also republish, depending on the application, so it's file sharing or some kind of caching layer and so on. There's a lot more in the paper when it comes to sort of caching, keeping buckets fresh, dealing with unbalanced trees, how you republish keys, implementation nodes, accelerated lookups. One thing that's pretty neat I just mentioned briefly, sort of this proof of consistency, where essentially we can show that we get log n average lookup time, and that data sticks around with sort of overwhelmingly high probability. And this is due to the sort of binary tree structure, the extra metric, and sort of the k buckets and the node uptime that I talked about before. But instead of going into that, I thought I'd talk about some Kademlia in practice nowadays. So first we have BitTorrent, and this is sort of the one that's used in BitTorrent. It's called mainline DHT, and it's a slight version of Kademlia. And it's used for finding peers. Has more than 25 million users. And essentially for trackerless torrents, instead of having this announce key with the pointer to the tracker URL, you have this nodes key, and that essentially has some nodes which helps with bootstrapping. One downside of this is that private trackers don't really want DHCs to be used, as they would sort of leak this closed membership set. So private trackers generally sort of don't allow it, and it's mostly used in public trackers, like for example Pirate. Another example is IPFS, which stands for like the Interplanetary File System, and it's using Kademlia, used it for a lot of things, used it for routing, but also primarily for sort of content-visible storage, so to create this sort of distributed file system. One problem with that is that you don't get very strong guarantees of persistence, because there's no incentive really to store all this data. For BitTorrent, this is partially solved with their sort of game theoretical tit-for-tat strategy that encourages nodes to share. And in the case of private trackers, there's a reputation system involved and so on. In the case of IPFS, the way they are approaching that is they have a product called Filecoin, where they're trying to build sort of incentivization on top of Filecoin, on top of IPFS, and that's trying to solve it by using cryptocurrency and incentives and disincentives, as well as some sort of fancy math for sort of proof of storage and these kinds of things. Swarm is a similar-ish model, but it's slightly different and works closer to BitTorrent with this idea of pairwise accounting. And it also has some insurance built on top. But both of these sort of products I just mentioned are very experimental and so on. Another product that's using it is Ethereum. So Ethereum is using this discovery protocol built on top of Kademlia, and doesn't use it to store values at all. It's just useful to finding nodes. I'm not quite sure how many nodes are in Ethereum, but maybe 10 to 100,000 nodes on the order somewhere there. And it's obviously a lot more expensive to run an Ethereum node than sort of downloading and uploading a torrent file. One thing to note is that there are multiple subprotocols of Ethereum. So you have different lifelines, and previously you had Swarm and Whisper and so on. And this is an issue with at least the version called Discovery v4 using Ethereum, where it can be difficult to find nodes of a certain capability because it's kind of like finding a needle in a haystack. This and a lot of other problems has led to a new version called v5, which is sort of under active development and is used in Ethereum 1 to some extent and will be used in Ethereum 2. And there you can sort of communicate these capabilities in this, you're generalizing the node ID so you have more information there essentially, as well as providing some topic abstractions to register capabilities and so on. So yeah, there's a lot more, and there's a lot of different products that are using Kademlia or Kademlia by design. Right, so we're going over sort of what a DST Kademlia is and why, where it came from, kind of how it works, briefly on some applications and so on. And I would say it's a very kind of elegant and practical design, very implementable. It says a lot that it's, compared to other DHTs, it's been implemented and used a lot. And it's definitely not perfect, like there's a lot of issues. For example, there are various attacks like Sybil attacks and DDoS attacks and so on, but it's definitely, it's a good building block. And it's become kind of a staple in the peer-to-peer protocol design world, so it's hard to sort of imagine where we would be without it. Yeah, that's it for me. Thank you. As a link to the paper, I do research at BackNet, and my Twitter and GitHub is here. Yeah. Questions or things people want to discuss or bring up?
Mm-hmm. Is that one command will tell your peer to store 2 gigabytes of file?
It depends on the application. I don't think there's anyone that's doing quite that. I know in the case of Swarm, they have this, they're kind of building an abstraction that's beyond Kademlia, but they have this chunker. So you have files and then you have abstractions for like a file manifest, which is like the equivalent of like a Unix file, and then you can chunk it up into 4K chunks, and then you replicate that, and then you have a location where you store a pointer to all these chunks. But theoretically, you could do that. Yeah.
So then the paper mentioned that it's using the SOAR XOR method for distance application.
Yeah.
And I think it kind of emphasized that it's a topology.
Yeah.
So could you talk a little bit more about it?
Well, it's a good question, and to be honest, I haven't gone too deeply into these other types of metrics. What I do know is that like it seems obvious, kind of, but I think that's kind of part of the elegance that it wasn't obvious when they came up with it because no one had come up with it at the time. In terms of other metrics that came out from like very respectable sort of research and so on, with code and paste and so on, my understanding is that they usually lack some properties, so they don't have unidirectionality, for example, or maybe they don't have symmetric distance and so on. So maybe there was like my understanding is it's kind of the insight maybe is to actually use a formal metric to note distance, so some kind of mathematical rigor that maybe wasn't part of other papers. But I've heard that like there are other types of metrics that it can be used as well. And I think there's some designs that are using it, but yeah.
Thanks.
So I'm trying to wrap my head around how this is used in BitTorrent, which is sort of what I'm most familiar with.
Mhm.
So in the Kademlia protocol, the node ID, does that have like the IP address so that you can actually communicate, or do you have to implement that kind of yourself?
So node ID is literally usually just a hash, and then with you have the address, right, which is usually IP and UDP. But it could be something else, like any type of address that allows you to reach a peer.
And that's part of the protocol, or that's
It's part of the protocol, but in the case of BitTorrent, they have a version called mainline DSC. I'm not exactly sure what the differences are in that protocol, but the general idea is the same, where you have some ID that's a hash and some address. Maybe you have some other information there, but essentially that's it. Because you want to be able to have information about nodes without actually knowing how to reach them, kind of. Does that answer your question? Or maybe not.
So, yeah, I guess I'm still not sure. Like, doing a bootstrap, this kind of thing. So you said a BitTorrent, that's in the torrent file. It has some node IDs there. And it also has like IP addresses, so you can chat with them. And is that part of the protocol, or that's like
No, I think they're there, right? Because the bootstrap nodes are usually publicly connectable, and at least the way we use them, I'm not sure exactly in BitTorrent, but the way we use bootstrap nodes, it's called like enode, and it's an IP port and node ID, and the node ID is cryptographically secured, so it corresponds to a key pair. That's how we use it. And I imagine this bootstrapping process is similar, but I'm not 100% certain.
Right. So like in the protocol, when you ask the nodes that you know to find another node, they will also return.
Yeah, exactly. So that's part of the return payload, this triplet of sort of an address and a node ID. Yeah.
Can you elaborate more on the usefulness of symmetric distance?
Usefulness of symmetric distance. Let me see. What was that again? That was not off the top of my head, but there are cases when I think if you don't have that, I'm not sure you would get sort of the same neat design with binary trees and so on. Like they kind of tie together. Like it's hard to get one without the other. That would be one way of answering that. Like I think in the case of code or something like that, the sort of topology mental model would look different. It's not a great answer though. Yeah, I don't think you would get sort of the same, be able to get the same kind of guarantees. I think that's the answer. I think it also impacts unidirectionality, so you wouldn't be able to do as much caching, for example. I think. We have a whiteboard, so I mean we could, but like if you, if it's not symmetrical, then I'm not sure you could actually, I don't think you can get unidirectionality. So there would be two distances, right? The distance between x and y. The distance might differ depending on which order you put them in, which is generally like bad in lots of math operations, right? So if you don't have unidirectionality, then it wouldn't converge on the same kind of lookup path. I think that's one of the consequences. There are probably more, because it's also like a triangle inequality that falls out of this. And I think if you don't satisfy that, then that might impact sort of the proof, consistency proof, and so on. But I don't have a detailed answer for you. But that would be my hunch in terms of why that's needed. Maybe someone else knows.
In your example, that would be like saying if the distance is not symmetric, what you're talking about, where like if I'm going to try and find someone in Europe who knows someone in the UK who can find my friend in London, that would no longer work, right?
Yeah.
And then now you can't do this.
Yes.
You can't find them.
Yeah. And I think it has to do with how it's doing with the direction. Like I forgot. I think the code paper essentially has this thing where it's going one direction, so it's like a ring, and then it's just different if you start here and you start here and go here. That's a different operation than going. You imagine like a clock going here and here. Any other questions or comments? All right, cool. At EF, and he's going to talk about profiling and de-anonymizing Ethereum users.
Thank you very much.
Yeah, thank you, Oscar. And yeah, we are talking about yeah, we're kind of being a detective today. We're trying to de-anonymize some Ethereum users just from their addresses. So first, this is a paper just published 2 weeks ago, I think. And then I have a friend here, is one of the authors. And why choose this paper? Because currently I'm working on some privacy solutions, and it's better to know how to break the privacy of existing tools, and then we have a better idea how we should build a better content privacy solution. So what's this paper about? So this paper identifies some like quasi identifiers to identify if two addresses they are from same owner. So this is because Ethereum is account-based model. So it's actually encourage users to reuse their account to make transactions. Unlike Bitcoin or Zcash, they use unspent transaction output model. That UTXO, which has more privacy because you don't reuse the same source of the balance. So existing privacy or the anonymization research focus on Bitcoin or Zcash because they are more privacy focused blockchain. Ethereum, this is the first one that did some data analysis and evaluate Ethereum's privacy. So those quasi-identifiers are kind of the activity, transaction feed, and transaction graph. And the second thing the paper do is to identify some heuristics to tell which deposit and withdrawal addresses from the Toronto cache are actually from the same owner. And yeah, we'll look into that later. And the third one is the one fingerprint attack on Ethereum. And last, I think this is the most interesting one if you're an engineer, because the author collects a lot of data and then did analysis on those data, and the source code released on GitHub, and it's very reproducible. So you can clone the repo and just run the script and reproduce the whole analysis process in the paper. And so, okay, so if we are trying to develop an algorithm to tell if the address, let's say, we have an address A1, address A2, and B1, B2, C1, C2. And they are actually from the same owner. And how would you design an algorithm to tell this kind of fact? So first, you must have some like ground truth. You must have some like existing two addresses. You already know they are from the same owner. So the author they download a lot of Twitter data, and they try to find if somebody tweets their ENS name or addresses, So you know they are for the same Chih-Cheng account. You know those addresses are the same owner. And also tornado cache, because the author developed the heuristic to identify which withdraw and deposit accounts are from the same owner. So we also have some transactions on the tornado cache that we can use to develop the algorithm. And humanity DAO, who remember humanity DAO? Okay, so it's a sad project. Sorry. Yeah, but it's a project trying to make identity from cryptocurrency users. Let's simply put it like that. And then so you have accounts with your real Twitter name or something. But because you only register one account on Humanity DAO, so no data is used in the ground truth pair. And yeah, let's talk about more about tornado cache or mixer. So in Ethereum, your transactions, let's say you get some ethers from an exchange, and then remember when you get some ether from exchange, you got KYC, you got like passport and your ID card, and you send a photograph to the exchange. And so exchange knows your address, and your ether balance, and who you are behind that address. And you want to like, okay, let's move the address, let's move my balance, ether balance to a clean, fresh address, but no exchanges know who's the owner of the address. But you can only send to another address, but the other address can be tracked by a transaction from the source address. So the one way you can break that link is to use mixer contract. So a mixer contract is, let's say you deposit, let's say you get 100 ether, and then you deposit the transaction to the mixer contract. And then after a few days or probably a few months, you withdraw, you send a withdrawal transaction, but that withdrawal transaction, you don't send a withdrawal transaction yourself because you still need an address to pay ether, and then that address might, you need to get the address for another exchange which might be KYC. So you generate a zero-knowledge proof on your desktop, and then that proof proves you are you have already deposited some 100 ether into a mixer contract, but you send the proof to a relayer, and the relayer pay against for you and withdraw the funds to a fresh new address that you own. So your new fresh clean account has 100 ether, and which nobody knows who's the owner behind that account because you are not the only one who withdraw money from the mixer contract. There might be thousands of people withdraw on the same day. So you create some kind of anonymity from, like, you need to guess who are you from thousands of withdrawals. All right. So, but yeah, that sounds good. What can break this? We'll talk about that later. But let's focus on something else. So remember, we got ENS an address from Twitter data, and some ENS address can be linked to maybe one address or two addresses or more addresses, and the other focus on the ENS name who links to exactly to addresses. Because we only focus on a situation like this. We want to map to address to the same owner. So we just take the two addresses case as the ground truth pair. And then, okay, so we now have our like ground truth data. We now need some features or like clues to tell which accounts and which accounts are pairs. So we call those quasi identifier, and two of them are time of the day and gas price distribution. And if you list of timestamp for a transaction and make a histogram of time, you can see that there's a pattern in the like 24 hours. There sometimes the Ethereum is more active, and sometimes like people are sleeping. And then another clue is that different people have different behavior of their setting their gas price. So let's focus specifically on these two ENS names. And in each of these names, it has two linked address, and if you analyze its distribution of the transaction in hours, you see the same the owner. It reflects the owner's daily activity. So even there are two different addresses, but the transaction has same like timestamp pattern. This shows the same, and also they have like same gas price pattern. So we can use these two features to do some predictions. And the third quasi identifier is the transaction graph analysis. So when you send a transaction from A to B, this makes two nodes and H. H is the transaction itself, and let's say there's another transaction you send from B to C, and then you can draw a path like this to C and maybe B sent to D, and those graphs have some features you can extract, and then you can use those features to predict something. I'm not yet deep into those features because it's you have some good libraries to do that. You can do node embedding. You can tag a cluster. It's usually used on social network analysis, and it's called Karate Club. It's not Hate Club. Right, and then we got the features, and we got a ground truth. We now need some metrics to evaluate how good our predictions are. So know that the anonymization is a classification test. So the classification test is like I have a fruit which is round, and you need to tell me is it an apple or is it an orange, and I'll need to evaluate how many times you got the correct answer and how many times you got the wrong answer. That kind of test. So the paper uses average rank. That means given an address, let's say given an address A, and the algorithm will output some like, okay, the number one possibility is B2, and number two is C2, and number three is maybe A2. And you can tell the correct answer is number 3. So, so the first prediction has a rank 3, and maybe you got the second prediction, and the correct answer is at 7, and the third pair, the correct answer is at 4, and you can average these 3 numbers and to evaluate how good your algorithm can produce the like if your algorithm is really good, the correct answer is within like top three candidates. If your algorithm is really bad, you might have like your correct answer might be at the top 100 candidates. Okay. And then we can define an area under curve over that matrix, but I'll talk about this later. And then another matrix is entropy gain. So entropy gain is before you let's say you want to guess you want to guess a number. Let's say I now have a number in my mind. It's 1 to 100. Now you guess a random number, and you let's see how if you can get the correct number I'm thinking. So before I giving you any clues, it's a uniform distribution between 1 and 100. But if I tell you the correct number is between 30 and 40, so now your possibility narrow down to the 30 and 40. So before I give you some information, this is your a priori distribution. And after I give you some information, this is the posterior information. And entropy gain is like you can make this distribution into a number, and the new distribution is another number, and you subtract these 2 numbers and you get entropy gains. That means the more clues you know, more information you know. So because our task here is not to predict exactly the exact account of the pair, but here we are more like trying to evaluate how much information I can narrow down, and to systematically evaluate how your system can preserve privacy. It's kind of quantifying your privacy guarantee of the system. And so a best part of the entropy gain is that you can compare the entropy gain between 2 applications with different anonymity set size. Let's say you have a mixer that has 100 with floor or maybe depositor, and another has 1,000 depositors. Theoretically, if you have an index that says the mixer 1 is like 5, and the mixer 2 has that index 10, can you compare the 5 and the 10? But in the entropy gain, you can like subtract these 2 numbers, because the effect, the anonymity set size to that number is small. So you can compare even the mixer 1 and mixer 2 has two different anonymity set size, but you can compare their entropy gain. So, yeah. And so, okay, so here's what we got from applying the time of the day feature and gas price feature and other network features, and then we use different algorithms to crunch some numbers. And so if you use okay, I just need to explain what's the area under curve. So in a classifier algorithm, we care about your accuracy and false positive rate. But actually, they, given the same classifier, they are actually trade-offs. So let's say I have some like round-shaped fruit, and I cover with the cloth, and you tell me it's an apple or it's an orange. But you can, like, when I ask 100 times, you can tell me it's apple 100 times. And you got 100 accuracy on apple, but like 100 false positive on orange. So it's a trade-off. You can have lower accuracy and lower false positive rate, or higher accuracy and higher false positive rate. So when you evaluate a classifier, if the classifier is good enough, you use the area under curve. So the curve is this one, and this is a random guessing. So you always get the same true positive rate and the same false positive rate. But if the classifier is slightly better, you got a larger area under this curve. So this is the perfect classifier, which has 100% true positive and no false positive. It's like getting the correct answer every time. So we use the area under curve as a matrix to determine how our classifier perform. So if you only use gas price feature, you can achieve 0.6 area under curve. Remember, 0.5 is like random guessing, it's random guess. But with daily activity feature, you got 0.7. And with some fancy algorithms, you can get like 0.8. And if you combine those good algorithms, you can get a 0.85. So yeah, that's kind of one way you can evaluate how your system is de-anonymized. And yeah, here we talk about tornado cache. So tornado cache, there are 3 heuristics that are used to identify which withdrawal and deposit pair from the same owner. One is if you are sending a deposit from address A, and then you withdraw the deposit to address A, then you are doing the, like, this is stupid user. So this address A, this deposit and that withdrawal is apparently evidently the same owner of address A. Okay? All right. And then heuristic 2, if that deposit and withdrawal pair, they are like just coincidentally have same gas prices, and then we can consider it as a same pair. And the heuristic 3 is that if, okay, let's say you do a deposit right and you do a withdrawal right, but then you send some transactions from the withdrawal address to the deposit address, or you send from the deposit address to the withdrawal address, and then you still got links like this. So this is kind of stupid things that users do, but you can see that the first heuristic can identify like almost 800 of addresses. Like there are like two more cases, like they reuse the withdrawal address 10 times, more than 10 times. And then, and with heuristic 2 and 3, you can also identify a lot of cases because the mixer has different values. You can deposit 0.1 or 0.1 liter or 1 liter or 10 liter, and the author also analyzed for the all time range or the last week or last just one day. Then so this is how you can map the tornado cash addresses from the deposit to the withdrawal, and it's also the user who did this also decrease the anonymity set of the tornado cash. And then the last one is the fingerprint attack. So normally you, when you send a transaction, you set a gas price in your wallet, and the wallet usually gives you an option to choose how many G-Way of your gas price. But if you manually set your gas price, you might end up let's say I should. So weight is 10 to the negative 18 ether. One weight, and one gigaway is 10 power 9 way. So theoretically, if you choose the gas price from the wallet, you should get the 9 zeros from the last digit in a way. They don't affect your transaction speed, but you can you either set the gas price yourself, or you got a malicious wallet who sets some digits for you, and then they provide some information and they can stay in your account for a long time. And then you can so we can use that as a fingerprint, and adversarial can fingerprint your account when you send to a confidential asset pool, and when you withdraw if the fingerprints still stay in the withdrawal balance, so you can link this deposit and withdraw together. So that's a fingerprint attack. And the author also lists future directions of the research. One of them, the wallet are calculating gas price differently. So like usually when you use MetaMask, the MetaMask has if you want to set a gas price that's fast, medium, or slow. And then different wallets have different configurations. So when you can just check the gas price, you can see which wallet you're using. Or if you use it manually, you can get more easily identified. And also, the other is very interested in explore the network level privacy. So the peer-to-peer load has some tiny information of your transaction. So if your transaction like broadcast in your peers and they have some peer get a transaction fast and some get it slower. So you can tell there's a like you can infer something from that tiny difference. And then now Ethereum people, some are using relayers. Relayers are some for privacy reasons, like in a mixer we produce that we need to use relayer to send the transaction. Or some are for like easier to onboard users because if new user don't need to pay gas, the relayer pays for you, but relayers can have chance to de-anonymize user with some tricks. And also the browser privacy, browser has some trackers and cookies, and people are now like interacting with the blockchain with MetaMask and mobile phone. So they are all like attack vectors that can de-anonymize the user. So yeah, I think my conclusion here is that we from this paper we saw a lot of features and techniques that can de-anonymize users. So if you are an application developer, you might like trying to build some features that can warn the user that okay, maybe I can randomize the gas price a little bit. So, or maybe you can like tell the user to like your account is already exposed enough. It's time for you to use a mixer. And when you use a mixer, you can tell the user not to do the stupid things. Yeah, and yeah, that's the takeaway. Question? Yeah.
So a question on maybe cash. So one is, what if any is the difference between the Fed model for native cash and Wasabi in terms of Wasabi wallet for Bitcoin?
Wasabi wallet?
Is there a difference in terms of their Fed model or in terms of heuristics you can use?
Yeah, but I'm not familiar with the.
Okay.
Yeah.
Because of the account base, that sort of implies more. If that implies more heuristics can be used.
Oh, I see. Yeah.
That's really question. Do you know what the impact, like how many users are stupid in native cash?
Oh.
Like what proportion of transactions could not be identified with these techniques?
Wait, let me check. I think we can infer from this. Yeah, so the author collects like 2,000 transactions, but I'm not sure that's if that's the total transactions on Tornado. I think the real number might be more than that, but we like 800 of address reuse are detected. Yeah, so yeah, but I checked the paper. I think it's not like should be less than 50%. I need to check. Any more questions?
One more. Okay.
Are you aware of any solutions that implement most of what can be considered the best practices? Can you recommend, for example, a mixer or a wallet that implements as many privacy best practices?
I don't know about wallet, but if you are using torrent cache, I mean, privacy is not like you can achieve with like one wallet or like one application. It's like you need to think about the whole procedure of your use case, or otherwise there are some parts of like the analyzation opportunity that the application does not involve. Like when you use torrent cache, you should use like a Tor browser to like at least change your IP and then withdraw to different addresses and like don't reuse your addresses.
Well, we're going to talk to the statistics because I'm not sure I think we might be vulnerable to the fingerprint. I'm not sure the fingerprint attack. It's an easy fix at least to provide options to randomize gas prices. I don't know what to say to this. I had a question on I didn't understand there's an area under control for classification. You have false positives and false negatives.
Yeah.
But from my side, it's based on empirical data.
Yeah.
How can you know something is a false positive or false negative?
Okay, so yeah, okay, let me switch to that slide first. So the area under curve is defined by
like the concept makes sense, but how do you know something is a false positive if the transactions being studied are real world transactions?
No, it's the transaction being started. So remember we have address pairs.
Yeah.
Yeah. So like A1 and A2, they are from the same owner. But the algorithm, if you like, okay, the algorithm thinks number one possibility is C1 and number two possibility is C2 and number three is A2. So you have a rank here. And the area under curve, they use like something like all accounts I recommended and the correct rank of the account. So they kind of translate this into the area under curve matrix. So it's not in a traditional classification sense that like a binary output, but it's a rank output.
So in the sample that's used is ground pairs.
Yeah.
Okay, so you know.
Yeah, they use this as to evaluate the
Gotcha.
Yeah.
I have a question. Like, the last example talking about the fingerprint.
Yeah.
Okay. So that only happens when someone put a small amount of ETH in my account.
Yeah.
And when I move all my funds, getting tracked.
Yeah. That's what I think. But like I got some confusions about like I asked Mikera, like, let's say if my confidential let's say this is a mixer and it only allows me to like input exactly 100 ether, and then the fingerprint might not get through, right? Yeah. Because I withdraw exactly 100 ether, but in case that it's still trackable, but I didn't have the discussion finished. Okay, yeah.
So it's probably like if I never send all my patterns to another address, then it's hard to track, right? Because I would never send the fingerprint. I would just
Yeah, so the paper actually had a table and analyzed the survival probability of the fingerprints. So the more transaction you send, the more likely the fingerprint got removed. So yeah, but like within 50 transactions, the fingerprint has 21% of survival rate. And yeah, but I didn't include that picture because I think I don't understand the fingerprint enough to produce that. Yeah. Any more question? Or?
Everyone. Yeah, I'm going to introduce this paper, a solution to the socialist millionaires problem. Yeah, I'm presenting this because my current project is related to this algorithm. Yeah. Okay. So I'll briefly introduce this problem, socialist millionaires problem. So it's just a simple problem that two people want to compare whether they are the same rich or not. So and they don't want to reveal their actual account balance to the others. So it's actually this function. You can the problem itself is just this function. So the two secrets and you output the boolean, and that means whether they are the same reach or not with the secure computation. The secure computation means that both players should be convinced of the correctness of the result with this function, and neither of them will know more about the result. And there is another more general problem called millionaires problem. So it compares who is richer instead of whether they are the same rich. So as you can see, it might be more general and more difficult. So as long as we can solve millionaires problem, we can solve socialist millionaires problem. And there are existing algorithms that solve this millionaires problem, but and we can use it to solve our socialist millionaires problem. So if that's true, why we need this protocol? This protocol is more efficient. It only requires big O1 exponentiations, and it finishes in a few runs. And it provides fairness, so-called fairness mentioned in their paper. It means that one party cannot get the result if they prevent the other to get a result, from getting the result. So either both of them get a result, otherwise they don't. Both of them don't get a result. However, if we want to guarantee the fairness, our cost will be increased to O equal K. K means the security parameter of this protocol, which means the size of the private key. So I'm going to introduce the assumptions, and the assumptions used in this paper and the proofs. First is the notation. So Vn means the residue class or minor n, and Vn star means the multiplicative, so that's the type of group of the Vn. GQ is a group with a large prime order Q, where Q divides P minus 1. And hash maps a string, maps the data to PQ. Sorry. Oh, yeah, okay. P, sorry. P is the prime. I failed to mention that. Is that okay? And I will keep going. And there are some assumptions using this paper. For instance, discrete logarithm, DL, or group GQ. So we assume that discrete log is hard. Yeah. So everyone knows discrete log. It means given g and y equals to g to the power of x, it's hard to find x. Yeah. And DH problem, means that given g and y equals to g to the power of x1, y2 to the power of y2 equals to g to x2. It's hard to compute g to the power of x1 times x2. And the decisional phenomenon DH. Sorry, it's hard for me to reproduce this. To conclude, DDH, this one is easier than DH. DH is this one means it's actually the computational development. And then it's easier than the discrete log. So we assume that DDH requires DDH assumption. So which implies we also have DH and DL. So to conclude, we assume this is typical. And we also need the non-interactive proofs of knowledge. It is we use a lot of this kind of knowledge to ensure the users are following our protocol correctly. So every value has to the other party is the company with the proof. Yeah, I will just briefly go through the proofs we use here. So the first one is the proof of knowledge of a discrete logarithm. This proof allows the person to prove that given y and given g, y and g, and I can prove that I know the x, which such that y equals to gx. Yeah. And the proof of equality of two discrete logarithms. It's similar, but it just allows the users to allow one to prove that there are two group elements, y1 and y2, and also g1 and g2, and you know such x satisfy y1 equals to y1 to the power of x, and y2 equals to g2 to the power of x. Okay, and this is proof of equality of two discrete ordinates. It looks more complicated, so I'll skip it and I will mention it later. So these proof of knowledge is serving as a tool to make sure that users are following the protocol. The protocol itself. Actually, the protocol it has two versions. One is one is with fairness, and another one is without fairness. I'm introducing the one without fairness because it's simpler, and we can add the fairness later. So first, they have to for two entities to run the protocol. They first have to generate a group G2, and they need to decide the G1 and G2 from G2 is a group, and they will choose X and Y, which are the secrets respectively from Z2. So the first step, assume there's Alice and Bob. Q1 and G2 is shared publicly, Q1 and G2. And Alice has the message X, and it generates random XA and A. And Bob as well, Y, X, and B. So first they performs Chih-Cheng. GA equals to Chih-Cheng. And they get a shared secret G3. And in this process, a proof of knowledge of discrete law is imposed because it allows, for example, Alice to Bob. It allows Alice to prove that Alice knows such XA, which makes GA equals to G1 to the power of XA. Yeah. Is that okay? Yeah. I'll move on. And then step 2, they're exchanging the PX and QX, PA, QA, and PB. Yeah. So it's just an intermediate parameter. So we're exchanging that, and PA equals to this, QA equals to this, and then they also have a proof for this. Proves that they really know the secret they used to generate them. So it's based on the proof of equality of discrete coordinates. Yeah. Is it okay? And then P and Q will be used to generate R, and they will exchange R, A, and RB. And this one, as you can see, RA equals to QA divided over QB and to the power of XA. And Alice, you can see here, Alice sent this to Bob. So Alice needs to prove that this exponent XA is the same as the one used to generate GA. So proof of equality of discrete laws is used to generate such proof. Yeah. And then they exchange the R. Then, with the exchange R, they can generate RAB respectively. And then they can check whether they can check the result on their own. So how to check the result? They compare whether RAB equals to PA and PB. So RAB actually equals to this one, this 2 1, and and PA over PB is this. So for them to be equal, this should be to them to be equal. This one should be even in between. So x should be equal to 1. Yeah. Is there any? Yeah. Okay. And the fairness. So the protocol I just introduced is the one without fairness. If we want fairness, we need to modify that protocol. First is in the step 2, which is the one we compute PA. We need an extra value E to compute PA, and also another random value F for Bob to compute PB. And then in the step 4, when we check in the step 4, which is this, we are checking whether RAB equals to PA over PB. Instead, we check RAB times this one. We check this. So in order for us to check whether this is correct, they need to exchange E and F first. So Alice is the F from Bob, and Bob is E. They release E and F bit by bit, and therefore only Alice can only know one more bit of F than Bob knowing E, because they release the bits and the EF bit by bit. Yeah. So therefore, the time complexity is all big O K, because EF is in K bits. Is there any question?
What is fairness?
Fairness. It means either both of them get a result. Otherwise, none of them get a result. Yeah. So in this case, if Alice doesn't release E to Bob, then Bob doesn't release F as well, to prevent Alice from getting the result. Because as you can see here, AB, E, and F do know whether this to know the result of this equation.
But they're always the last one to exchange. Let's say the last bit, then Alice saw the last bit, then Alice decided not to send it.
Yeah, but and then you can easily guess the last bit.
Oh.
Yeah, 3/4. Yeah. Question? Yeah. So I just finished introducing the protocol, and the conclusion is it allows one to fairly check the equality of two secrets X and Y to solve this problem. And the time complexity without fairness is big O 1, but with fairness is big O K. Yeah. And the reference, and the implementations. I just want to advertise mine. Yeah, that's it. I might miss the answer.
So I think this is used like in off-directed messaging.
Yeah.
Like what's the application that you said it related to the project you're working on? What's the application?
Yeah, the application is called meetup, which is a private order matching system. So, how to say that? We want to advertise the education about it. How to say that? So in this system, you can advertise that you are interested in some trading pairs like BTC, USDT, and the amount, and yeah, and the others. But you don't want to reveal your price to the others because it might allow others to manipulate the market, something like that. So we use S&P to compare the price between the users. This way, users can only know whether the taker and the maker, they can only know whether their desired price is the same. If the price is the same, they match and they can proceed the trade. Yeah.
Can you generalize that? So you have the millionaire problem, which is if one is rich than another, and then socialist is equal. Can you define a range? So if you're within 0.1 point, then I'll accept your price. Is that mathematically possible? I'm not fluent enough. Like, can you do that type of operation?
No.
Okay.
Yeah, you can just compare whether
It's exact match.
yeah.
We're going to avoid that loss.
Yeah. So I'm not sure whether we can do that with the millionaires problem. I mean, another a more general one.
Can you do free? So you do one is equal, and then you have three of them, so you do them in parallel. And then you get like, if it's less than, you fake that your price is 0.1 times higher. Then, I don't know, maybe,
You can do your range out of there if you're willing to share a range, right? And then they can give some information themselves and then they'll
I'm not really sure.
Let's say you can call the price as signature.
Yeah.
And then, let's say you want to check if your future price is within range of +5 and -5, and then you need to have 10 times of communication and doing that process. Because it checks the equality on the history of
Or if you have less, you can do the less than or greater than. Right? If you submit two of them, you should get the equality, you get true or false for range. Like if you have one bit, and then you have another that's basis point higher, and then you check if that is higher or lower. So maybe the dollar one, the average one, whatever, is not higher, so it wouldn't be accepted, but the other one is within range. And then you just, the actual settled price is the one in the middle, maybe, I don't know, lower.
But when you don't know which one is higher or lower, you just know that
You can communicate that. You can leak that information. But this is my higher bid, this is my range, my higher bid and my low bid. But maybe you would have to wrap it in some certain other stuff to make sure that it's not used. That's true. You can use that information to undercut someone, maybe.
Yeah, I'm not sure. I need to think about it. any other questions? I think that's it.